Hey,
Hey guys, hey, well, nice to see you again.
nice to see you, Kwan.
Yeah, I hope it's okay for me to speak here. I don't know what's I guess it's live now. Is anyone?
It's both here and on YouTube. So if you're having concerns about some stuff that shouldn't be too public, we can turn off the stream.
No, it's fine. I'm just thinking if there's any talk ongoing at the moment, and I'm at the right
Ah,
time.
so yes, so you're at the right time. You're
Yeah.
actually early. Um,
Okay, that's good.
the your talk is
So
16:15.
so now it's
Now it's
16:00.
yeah.
Okay,
Um,
15:59.
yeah. So if you need a coffee or something.
No. I I think I got your email saying that you should come in a little bit early just to check the.
Yeah, we thought like if people, some
Yeah.
people have issues with the PowerPoint and stuff. So if you want to try sharing the screen and things.
Yeah, sure, I can try. Yeah, let me also put in full screen just to test it out.
Yeah.
Um,
Well, the event going on right now is on a different platform,
okay.
programming tutorial, which is a bit more interactive. So that's why it's somewhere else. It's on a Gather. Don't know if you've seen.
Mhm.
That's why not so many audience members are here, but they should trickle in.
Are you seeing the right screen at the moment?
Yes. So
Okay, so that's a.
yeah, looks really spacey.
Okay. Yeah. Okay. Spacey. SpaceX inspired.
Is it?
Yeah. No.
Are you allowed to say that in public? No, will they
No,
sue you?
no. No, inspiration is good, right? They inspire people.
Yeah, that's yeah.
So how's the summer school at the moment?
It's good. I think it's we had
Mm.
Andreas Wallraff and Vincenzo Savona on Monday, and this morning we had David DiVincenzo and Jonathan Holm.
Right.
And then yesterday there was also two invited talks, and one of them was this kind of IBM head of IBM,
Direct.
head of IBM research directorship.
Yeah. Mm.
It was kind of high level, but still interesting, especially if you like
Right. Okay.
the broader public. And then the other talks were really lectures on things, so also quite interesting. And when we stream them on YouTube and then just leave the video on YouTube, like the live stream,
Right.
like hundreds of people watched it. So quite some resonance.
Yeah. So you were saying that you have this so a lot of applications, but you screen them and you only allow certain people to come in, or is it now
Yes.
that it's online that.
In the beginning, we want to do it in person, and then now when we put it online, we thought, how many people can we like realistically handle in Zoom? And we wanted to have people in Zoom that ask like useful questions and stuff. So we still restricted the number a bit, but then everyone else just got a YouTube link, and it's not just the stream. It's basically yeah, just to avoid like I don't know. Yeah. So the other talks were like maybe 50 people in the Zoom.
Okay, yeah, that's quite many too. And I haven't actually met Maxwell. Nice to meet you, Maxwell.
Hi, I'm going to talk with audio because we're in the same room and I don't want to make an echo.
But yeah. Okay. And Francesco was so I can see the video earlier, but then he's probably busy.
He's probably getting coffee as well.
Yeah.
He's probably in the Gather.
He's still in Gather, yeah. I saw you had a press release recently.
Like yesterday, you mean?
Yeah.
Yeah, I'm gonna show that. I just remembered, so I just cut and paste in the the slides. You mean the one from VTT, right?
Yeah.
Yeah. It's yeah. Happy customer is a good thing.
That's nice. That's nice. It seems like everyone is installing quantum computers. There was also this press conference by the head of IBM.
Yeah, in Germany, in Fraunhofer, I think they installed something there, and yeah, it's great. At least it's great for the community. Like people are willing to fund these big projects, and of course, eventually there will be some use, but we just have to get there. And I don't know what's the time frame or like time horizon for this to happen, but hopefully soon. And yeah, I think the summer school that you're doing is actually pretty good because it trains like a lot of people, right? It gets this interest going, and then ETH is like one of the best places to be for superconducting circuits and also ion traps. And I think yeah, I don't know how many. I was talking to, I guess you know Paul and Moritz.
I know Paul and Moritz.
Yeah. Okay. So yeah, they are the summer interns here from ETH, and then yeah, he was saying that the master's program is actually pretty good there as well. I think you're getting like even hundreds of applications, and then you can only take
engineering program that they have since 2 years here. I think is people are actually applying a lot. Some of our master students are from there. Like more and more actually come from the quantum engineering people.
Yeah, and it's great that all these like top research groups are supporting this, because I would imagine it takes a lot of time and resources from them, like training up people, and then they have to leave after a year or two.
It's always somewhat of a trade-off, but I mean,
yeah.
I guess in research groups, students also contribute, right? So yeah, and then we send them to you, and then we can keep training them.
Yes, we have at the moment in the company, I think roughly 10 PhD students working, and yeah, we are taking interns, but there's only a certain capacity we can, because otherwise most of them will come in without like proper projects, and we also don't want them to be disappointed, like not doing anything.
Yeah, of course.
Yeah, but it's also a good training for us how to be prepared for such things, because we are we are startup, and we don't have like these decades of experience in the academia. Yeah, cumulatively yes, but still there's a lot of overlap.
Absolutely.
So how's the traveling to Switzerland right now? I think most people are already vaccinated there.
In Finland?
No, in Switzerland.
In Switzerland. Oh yeah. It's starting. It's the vaccination. It's getting somewhere, but it started very late. So I'm vaccinated, and most people in the group are vaccinated once.
Yeah, I just got mine last week. So yeah.
But since it's Switzerland, every canton is different.
Oh right, yeah.
Yeah.
Everyone vaccinated. Some
if you go 20 kilometers in that direction, completely.
Yes, it's the same here too. They have to be politically correct.
And then, so I guess questions. We have this Q&A block in Zoom. You should be able to see it in the bottom of your screen.
Okay.
If someone asks a question, feel free to answer them in the end or in the middle, whatever you like. I can also point them out to you in the end. I guess I'll remind you.
Oh, okay, Q&A.
Before the.
Yeah, I didn't really. Well, actually, I just take slides from here and there, and then just prepare everything. So hope that I can keep within time. I think it's 30 minutes, or is it
45?
45. Okay, well, that's quite long. Yes.
Yeah, including questions. So.
Yeah. Okay. Yeah, I'll try my best.
Of course. Yeah.
Yeah. So you are. I guess Maxwell is also doing your PhD at the moment, and are you guys finishing soon? Or Not yet. Oh, yeah, it's like, yeah, it's the taboo question that I should not ask.
No, we're not there. We're not at the point where the question becomes rude yet. So I'm in my 3rd year. We built up a lab here.
Yeah, that's the most difficult.
So basically, like we're building up stuff, and we're just starting to really measure interesting things. But I'm not close, I would say.
And I'm really not close. I'm in my 1st year.
Yeah.
Okay.
Yeah.
Yeah, but once you get the like good results, you are just basically writing every day. Yeah.
I hope so. I can't wait.
I mean,
yeah, it's also, if I remember correctly, last time, yeah, I also did similar stuff. Like first 2 years we were setting up a lot of things. There's no processes, nothing, and then there are, of course, a lot of failures in even trying to get the devices. Was quite yeah. And then after that, when you have results, you have one sample that keeps on pumping out all the results that you want, and then you'll be writing to the point where you really cannot look at. Okay. yeah, you cannot even read the sentence that you write anymore.
Just was writing to people.
Yeah.
But he's writing to everyone.
Yeah.
I'll text him.
Ah, that's Needy.
Needy. He's the next session. Yeah.
Yes, his next one. I hope I didn't mess up the time. So.
No, that's okay.
Hey, Needy.
How are you?
Good, thank you. How are you? Is it very early?
No, it's fine. I'm just checking that everything is fine on my side. So I'm glad it is. So that's perfect.
Yeah.
I don't know if you two guys know each other.
I don't know Meaty, but I know, yeah, Cambridge Quantum, of course. They are,
of course.
Now, also great news from them, having this joint venture with Honeywell, and a lot of fresh funding coming into the company as well. And
I'm sure lots of people will ask you questions about that later, maybe.
So let me step out and come back in actually 45 minutes with Simon. I'll update him, and then we are good to go on our side. And nice meeting you.
Yeah, nice meeting you. Yeah, I'm gonna tune into your talk later, but I don't have this non-panelist link, so I cannot tune in as an audience, basically. Would that be a problem or no? Okay, it's a secret. Anyways,
if you really want.
Yeah.
Yeah, I know sometimes so we basically listed all the email addresses of the speakers for the webinar to recognize them and put them in the panelists section, just so they don't get stuck in and then we don't see them, maybe, you know. I don't think Francesco heard you. It's funny though.
So I guess this summer school is an annual program, and it just started this year, or was it like already ongoing before?
EPFL and ETH had this, I guess, leftover budget to finance new summer schools, and we wrote an application and got like one of the projects. Yeah, so it's new. We never did it before.
Okay.
Hi, Francesco.
Hello.
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 Francesco.
Thanks for joining.
Well, thank you for organizing your invitation.
We are honored.
Yeah, same here. We are very honored to join this inaugural summer school.
So we are almost there, right? In 2 minutes, we should start. Great.
Yeah, so Francesco is working in Lausanne, more on the software side.
Yeah, both quantum algorithm, but also like a theoretical simulation of the hardware.
Oh.
Where hardware should be like a defect in semiconductors, even if now they are not regarded as qubit anymore. But 3 years ago, when I started, they were candidates as well.
Semiconductor, you mean spin qubits?
Not really spin qubits, like a nitrogen vacancy center in Diamond. These,
okay, yes.
That are now very used for quantum sensing. Before they were considered also possible qubit, but they're not running very well now, let's say, on that point of view.
Yeah, I mean, it's very hard to place it at the position you want and control it.
What happened, guys?
Yeah, I guess it's time. Maybe I can also start by sharing my screen first. This one. Okay, by doing so, I can no longer see the Q&A. Can I? Oh, yeah, I can.
Yeah, it's just that the panel where the Zoom control panel moves somewhere else when you share a screen. But you've figured out.
Yeah, so if I put here to block this, I cannot see people's faces. I need another screen.
Okay, then let's get started. So I think people are maybe still trickling in, but I think if they missed the first 2 minutes, it's okay. Yeah, well, so it's a pleasure to introduce Dr. Kwon Tan. He's the CTO and co-founder of IQM Finland, which is, I guess many of you know. Kwon graduated with a PhD in electrical engineering from University of New South Wales in 2011. And after spending time as a researcher at Microsoft in Sydney, he came to Finland and worked as a postdoc and then as a research fellow on superconducting qubits. Finally, in 2019, he co-founded IQM with the mission to make quantum computing a reality. Give it away.
All right. Yes, thanks a lot, Uwe. Thanks for the very nice introduction, and also thanks for the invitation to your inaugural summer school. This is, of course, an honor for IQM, and I guess since this session is about startup, I would like to use the opportunity to introduce the company, and then also talk a little bit about the pains of a growing startup and what we have done and achieved so far, and what we look to do next. So basically, this is just an outline of what I'm going to talk about, and let's just start with the introduction. So as you know, as a company, you need to have a vision, and the vision of IQM Finland is to we kind of see that quantum computing would create completely new markets, and whoever that leads this sort of technology now, of course, will benefit in decades to come. And and IQM is very well positioned in realizing this vision, because we have, as you have seen in the news, successfully landed our first sales case, and then of course, as the investment into quantum is growing over time in Europe and other parts of the world, we see that this is a great opportunity also from a business sense, that we would start delivering quantum computers as products. So it is also IQM's vision to at least the first phase have this European leadership position, and then after that expand globally. Of course, also for a company, you have to have a really great mission statement. And so over the years, IKM basically started in 2019. We started building our mission statement. So this didn't just come overnight, but we started thinking, okay, what is something that you can use to inspire people in the company and also outside? And what is something that is also far reaching in terms of your vision? And what is something that's actually practical? So we came up with this statement that we are building world-leading quantum computers for the well-being of humankind now and for the future. So this is something that is what we hold dear every day when we come to work at IQM. So the another question that we get asked a lot is like, why now? Why quantum computing now and not like 5 years ago or 5 years later? We have seen like really great results coming from Google in their 2019 quantum supremacy experiments, where they use 53 qubits to do a random sampling problem that it's very difficult for it to be achieved computationally using classical computers. So the question is that, can we turn this random sampling problem into something useful? And at IKM, we believe we have the technology to do so. I'll talk a little bit more about this, what our strategy is, basically through co-design. And then also at the same time, we are building up the right team, the technology, and also the market intelligence, and also go to market strategy of how we deliver these kind of computers so that we can have a sustainable research and development and also expansion of the company. So as an organization, we have grown really quickly. So since July 2019, we have about 100 employees right now, actually above 100 employees span across 2 locations. One is in Espoo, Helsinki, Finland, and the other one is in Munich in Germany. So this pool of people, they are quite diversified. We have like 26 nationalities altogether. And so since we are also a deep tech company, we have more than PhD people with PhDs titles in the company, and 5 actually with professor level equivalent scientists actually working in the company. And at the same time, we are also training 10 PhD students within the company and taking in many very brilliant interns, many of them coming from Switzerland. So all these talents actually come from across the globe, as I've mentioned earlier, and then they are also coming from really good universities and also corporates. So the journey. So of course, the whole operation of IKM started in 2019, but the actual, back of envelope drawings possibly in a garage actually happened already in April 2018. And then during that time, we started thinking, okay, well, what is the way for us to actually, make quantum computers useful and also deliver it to customers in the future, or some enterprise customers initially, and after that to the mass market, so that people can actually benefit from the all the promises of quantum computing. And then this actually took quite some time for us to come together for us, like the co-founders, think of a really good story and how to go out and convince the investors. And so you can see that the time period is actually quite long. It's more than a year. And only in July 2019 did we close the seed funding round of, at that time, one of the largest in Finland. It's about 11.5 million euros. But of course, if you want to embark on a journey to build one of the hardest devices human has ever made, then this is really a very small sum. But at the same time, we receive a lot of support from our neighbors. Like Bluefors is one of them, that they already believed in us at the very beginning, even before we closed the seed funding round, that they would already start fabricating the fridges that we would like to have when we start our company, and actually deliver in really record time of about 2 months. And then we got everything started at that time. So we have the first fridges in September 2019 already, and the second one in November 2019. And this allows us to ramp up our testing and production facilities. And then back in March last year, we also established a subsidiary called IKM Germany in Munich, and this subsidiary actually is focusing on a little bit towards this co-design, which I will talk a little bit later. And then also at the same time, we are involved in a lot of grant applications, consortium, individual ones, because when you have this funding, it's not that you spend it, but you have to somehow figure out a way to capitalize on this funding. You get loans, you talk to a lot of this like Business Finland equivalent, like this, that supports all these startups, and try to attract as much funding as you can to do the R&D and also expansion of the company. And we are also quite unprepared, I have to say, at the very beginning. We started, in a lab, which we thought that, okay, we're never going to sell a quantum computer in the next 5 years. So let's start really small. And then before the end of the year, we already start to realize that, okay, we are outgrowing ourselves. So we have to move to a new facility, and we have to, shut down the fridges, move the fridges to even a new facility, and then we started everything. And we of course already have the process in place, because moving fridges is something that you would have to do at some point, because you want to deliver quantum computers to customers, and then it could be like cross borders. And then we started setting up everything, and then we again show our technologies, demonstrate our technologies, especially in this reset of the qubit, which I will show later. And then at the end of 2020, we also closed our Series A1 round, which is about 40 million euros, and that helped us expand even more. So since then, we have done quite much. So we closed also our first sales case with VTT. So this was an open tender, and I have to say the competition was quite fierce, and we won just very narrowly. And at the same time, we demonstrated our 2-qubit gates, received more public funding, and then we are also leading at this point a German consortium to deliver co-designed quantum computers to research quantum computers to some supercomputing centers and research centers. At the same time, we ramp up our sort of design flow and also the fabrication efforts, and we managed to control the quality of the devices coming out of our the shared clean room that we are using. And now we can achieve quite consistently high fidelities for our qubits, and also across like a whole qubit chip. So it's no longer a one single hero sample that we get running. And I'm also happy to announce that we internally are calibrating our 5-qubit processors, and we will deliver soon one of this system to VTT, to speak. And at the same time, there's a lot of going on also on the software effort. So initially we started as a hardware company, but we realized that, okay, you need some software as well, otherwise you won't be able to control your qubits. And we developed those in-house, and at the same time, we figured that, okay, if you want to design more and more complex, quantum circuits, you better have a really good design flow and automated design software. And that's why we happy also to announce that we have published this so-called KQ circuits. This is actually a design tool that we use internally in-house that allows us to design this and also route our qubits in a quantum processor quite efficiently. And at the same time, it has this 3D integration capabilities in there. And after that, we also integrate at the very high level with Cirq, so that people who have programmed circuits using Cirq can eventually utilize our quantum hardware as well. So now I switch gear a little bit, and I'll talk a little bit about IQM's approach to quantum computing. So how do we visualize our business strategy from the short term, medium term to the long term? So initially, in the very short term, our aim is to commercialize the early quantum computers, which we call research quantum computers, that might not necessarily help us achieve quantum advantage, but still, nevertheless, very useful to kickstart ecosystem and use for research and educational purposes. So this is exactly one of the machines that we deliver to VTT, and of course, seeing all the news coming out from Europe and elsewhere, you can see that there's a growing demand for such systems in years to come. So in the medium term, of course, we need to achieve quantum advantage, and of course, in the medium term, we don't foresee quantum error correction to be quite widespread, at least not for the next decade, that we can make something meaningful out of it. But the question is, can you then do something through co-design of hardware and software and algorithms, and see if you can achieve quantum advantage already with the a little bit higher end system compared to the ones that we have today. And this is actually an active effort from the company, and I'll talk a little bit more about this. And in the long term, of course, we still foresee that quantum error correction is needed, because that's when you have a general purpose quantum computer that you can solve pretty much all the things that quantum computers can very efficiently. So so this is like what I mentioned earlier. So the early systems, we use it to create a market for quantum computers. And then in the co-design systems, we look for expansion of the market. And then finally, for this universal quantum computers, we still foresee that it is not something that people would just install in their, in their offices as a desktop, but something that is actually quite suitable to be installed in high-performance computing centers. And therefore, we are looking towards integration of these quantum computers as a form of accelerator there. So just to give you an overview of the system that we plan to deliver to VTT. So this is our first reference case, and the aim is to deliver like a 50 qubit machine by 2023. And this project actually comes in 3 phases. So the first phase is that we will deliver the first 5 qubit system there, and then upgrade it to 20 qubits, and then in 2022, and then in 2023, get it to 50 qubits. So this is a substantial investment from of course, the VTT and also the government. And we're happy to announce, like a couple of days ago, VTT released a press saying that they find that everything is going smoothly, and then they are really happy. So it's always great to have your first customer as a happy customer. So yeah, like I mentioned earlier, as you can see here, there are more and more investment pouring into quantum computing, and this investment is actually accelerating as a function of time. So we see already in the first phase of this delivery of research quantum computers, it's a viable business model. Of course, this process is it's not as simple as you just go there and sell the quantum computers, but you have to talk to the people there and make sure that everyone, from the politicians to the academia to the industry, actually believe that this is something that's going to be useful for them. So this is like a huge effort in terms of business development also, and but we already have, with this first reference case in VTT, we have a sort of an idea how we could go in and propose a really good solution to all these different countries. So in the second phase, like in the market sort of expansion, where we want to try to achieve quantum advantage, we kind of have this idea, like the competition now is at more than 50 qubits, and their aim is to go all the way to the end to have this quantum error corrected computers that can solve pretty much all the different problems using the same machine. But in our case, like IQM at the moment is at 5 qubits. But then we kind of have to think of what's the other solutions that will put us in this niche market where we can say, okay, is there any application specific solutions we can provide to enterprise customers? Because enterprise customers nowadays, they don't want to solve everything. They just want to focus on certain topics like quantum finance or quantum chemistry, whatever that's relevant to them. And then and then in that case, we will find the sort of algorithms that would be able to solve their problem and also can be run efficiently in our machines. And then we start to design our QPU architecture so that it can be used to efficiently implement these algorithms. So, for example, in this general machines, people typically have this square lattices. In our case, it could be something that, for example, mimics a molecule. In a way that you can solve, like you can do quantum simulation already with whatever technologies we have at present day, right, in the near future. So that's the idea. So of course, to initiate conversations with enterprise customers, it's not so easy because most of them, they are at different levels of understanding of quantum technology. Some of them, they already have internal quantum teams. Some, they just want to know what's out there. Is this a scam or something like that? So in our business development and marketing side, we have to go directly into the enterprise customers and start conversation with them at different levels, so that we can identify, okay, in their technology roadmap versus our technology roadmap, is there some crossing points where we can say we have certain technologies that we think we can help in their problems. Like, for example, simulation of certain chemical molecule is one of them. And then we distill those problems into some algorithms, and we do some initial simulations to see if we can achieve any advantage, and then go through this process with them. And at some point, make some proof of concept quantum computers that we show that we can achieve advantage, and then at some point also discuss with them, is that something that you would like to see towards advantage? So basically, they will put in more investment at different phases to push it to some something that's useful for them. And of course, this sort of business model is something that we are creating as we speak internally. And of course, different customers, they have different needs, different investment capabilities, and we are trying to tailor this to different customers at the same time. So in the last phase, of course, HPC integration is one of the big things. Even now, like if you go to big HPC providers like Atos, people have been talking about having quantum computers as an accelerator, because they have been using like GPUs for accelerating certain computation already, and even machine learning chips. And then the next big thing, of course, is quantum. And of course, this is not as easy as integrating like classical systems in there, because you have to worry also about these classical quantum interfaces. And is there some hybrid algorithms that you can run such that some parts actually go to classical computing and some goes to quantum, and then you merge them together to have a meaningful result. And then, all these interface technologies are of great interest to all these HPC providers. And of course, then we are in a good position, I have to say, being one of the scalers in Atos scalar programs. So finally, in this aspect, I would say having partners is very important for a startup, because it is not only something that says that we are doing business with someone, but we also get like some big names to actually vouch for our technology. And this is something that's not very easy, because you kind of have to make sure that you have a technology and a story that makes sense for all these big partners. And this is something that we initially struggle a lot as a startup company because, you know, nobody knows IQM, nobody knows what we are doing, and very few even knows what quantum is about. And we spend a lot of effort in terms of the, you know, initial discussion, also mutual learning from each other, and at some point finding a common ground where we can start developing these technologies. And yeah, so finally, I would like to switch gear a little bit to talk about the latest results that we have. Again, this is not something that's going to be very coherent. I'm just throwing all the results that we have because we are developing so many things in parallel. And just a few highlights that I'm allowed to show here. So yeah, so the sort of results is divided into two sections. One of them is about hardware, and the other one naturally is about software. And the first case for hardware is that we have this sort of unique selling point in the technology within the company that we would like to use a so-called quantum circuit refrigerator as a form of reset of our quantum bits. And of course, this goes back to 2017 when we discovered that we can use this so-called NIS junction, so normal metal insulator superconductor tunnel junctions, and you put the pairs of them in a resonator, in this case, a superconducting coplanar waveguide resonator. And by just tuning the voltage across the junction, we realized that we can have this like photon-assisted tunneling absorption of the photons from the cavity or the resonator itself. So if you look at this energy diagram, you can see that a certain bias, there's no tunneling current except for when you have photons in the vicinity or in the environment that will kick the photon tunneling between the superconductors, superconducting tunnel junctions there. So here, of course, in the graph to the right, you can see that as a function of bias across this junction, at which point where this sort of absorption becomes maximum. So of course, naturally, in this case, in our engineered environment, it is quite close to the gap of this NIS junctions. So with this idea in mind, what we do is that we then integrate this whole system into a superconducting transmon qubit. And as you can see here, initially, you know, what you do to show that you can actually do this absorption of single photons in a qubit is to excite a qubit naturally, and then do a sort of drive to the quantum circuit refrigerator, a fast drive, and then that would actually allows you to absorb the photon from the qubit when it's in the excited state. So here you can see that in the graph, when you don't do any excitation to the QCR, then basically the qubit remains in the natural decay state, but when you have this reset pulse going to the QCR, you immediately reset it to the ground state. So this is an ongoing project, and even at the very initial experiments, we find that we can do already quite high fidelity for the reset, about 96% and below 100 nanoseconds. So of course, there's a lot of optimization that we can still do. And this is something that we're working on as we speak. So the second hardware results I'd like to show is that, yeah, as I mentioned earlier, we have been ramping up the production of our quantum processors. And of course, naturally, you need to have consistency of the coherence times across all the qubits. And we have successfully shown that we can consistently manufacture many single qubits on the single chip to have really high or relatively high coherence times. And that, of course, allows us to sort of perform randomized benchmarking and, you know, extract our single qubit native gate fidelity. And in this case, it's like 99.91%. Of course, there are room for improvement, and we believe that it's at least going in the right direction. Of course, like to have quantum processors, you not only need to have qubits, you have to couple them together, but also you need to have like a really good readout optimization. And typically in readout sense, we need to have a quantum limited amplifier. In this case, it's the 2PA. And then after that, you have this like amplification chain going up to the room temperature. And here we are constantly improving this because readout fidelity is one of the key technologies that we need to excel in. And the fidelity we get so far with all the two-part technologies that we get from VTT is about 98.4%, and this is at the threshold that we are limited by the coherence of the qubit itself. So room for improvement, yes, but we are slowly getting there. And of course, like in any qubit technology, you need to have you need to show that you will be able to couple two qubits together and perform two qubit gates. And here I've shown a device, a 3-qubit device, where you use the middle qubit as a coupler. And with this sort of tunable coupler and tunable qubit architecture, we have shown that we can effectively turn off the coupling or on the coupling between the two qubits just by driving the coupler itself. And with all these fidelities that we have for this multi-qubit device, we have achieved quite high, relatively high 2-qubit gate fidelity. So this process tomography is about 97.3%, and it's still not at the stage where it is coherence limited. We believe that there's some leakage to the the middle coupler, but at the same time, this is something that we are improving quite much. Of course, our final, qubit, 2-qubit gate or multi-architecture is not the one that you've seen earlier. That's just the traditional XMONs. But with the new improved design, we expect to push this number even higher. And then switching gear from hardware to software. Software is, of course, very, very important in terms of like designing your processes to controlling them. And one of the critical things inside the company is that we realized very early on that you need to have a really good design flow within the company, from the actual design of the processes to fabrication to characterization. And this cycle has to be as efficient as possible. And if you simulate something that is not good and then you start fabricating them and measure, typically you see a lot of stuff that you don't understand, and that's pretty bad. And in our case, we are trying to improve this. We are trying to create our own so-called synopsis or cadence equivalent of our design flow, and happy to show that some these results actually is very good agreement with our measurement data, and we can see that the coherence times actually agrees really well with the precise limit that we anticipate from our simulation. So this is like of course what we have now is a little bit more advanced, but this is what I can show at the moment. And finally, for software, we have also developed this KQ circuit. So this KQ circuit is actually part of our design flow that we actually have open source. I think it's beginning of this month. And the aim is, of course, like to benefit the community as a whole, to utilize the software to do the quantum circuit design. My personal experience is that I've been to so many labs, and I realized that there's a huge need for such a software, but people are typically just hack and slash, hack all this stuff together, and also at the same time spending a lot of resources making not so scalable software. And in the company, we figured that since we are using this to design our quantum processors, why don't we just open it up so that people can also use it? This actually also is very useful in the sense that it allows wafer scale photomask generation, parameterized, of course, so that you can easily make your photomask and then do your fabrication in no time. And as I mentioned earlier, this is exactly the same technology we use in our company. So you can expect like active development and support from the IQM's design and software teams. So anyone interested, just check out the link below here, and then yeah, and any questions or anything, feel free to contact the team at IQM. So finally, one of the main thing of being in business and startup is that branding is also very important. So this is like very important for any business, and also quantum computing startup. It is even more so. I have to say that all these medias that I put here are mainstream media. These are earned media. We are not paying them to sort of feature our stories. And of course, this is very important and also a very effective way to get our name out there. This will create sort of a positive sort of feedback loop for the company, not in terms of only on funding, but also on collaboration, and also getting really good people to join us, because we are getting a little bit more well-known than before. And then, of course, we have also garnered a lot of media headlines in the past year within the company. I have to say that we have also really good Series A investors coming into company. Most prominent one, of course, is Helmut Jägel from BioNTech. So typically in a startup world, you see a lot of investors. They have a lot of money, but at the same time, you have to always think, is that a good idea? Because you have to have people that not only comes into a company just for the short, break where they can get a lot of ROI in a very short period of time, but also at the same time, you need to find people that can have a vision and really invest in the technology and believe in the company. And yeah, so of course, BioNTech is a very similar case in the sense that the investment in the company actually started in 2008, and the reward actually comes quite much later. So Helmut has this experience, and hopefully it will bring us to the next level in terms of the sort of growth of the company. So that's I think that's it from me. Hope you enjoy the talk, and if there's a question, happy to answer.
Excellent. Thank you, Quan. Perfectly on time as well. And maybe I can start off with a question from my side. So I was actually curious about the quantum circuit refrigerator. I'm sure you did a lot of simulations on these, and was wondering if the reset on the qubit, how it compares to what people do sometimes with the FPGA reset, or so measuring the qubit and flipping it, or some unconditional reset protocol that uses non-computational states and that decay perfectly.
Yeah, so yeah, that's a very good question. So in our case, it's an unconditional reset. So yeah, basically, you can reset it from any arbitrary state, and it's basically absorption of radiation from the actual device, and it's in very close proximity to the device. Therefore, it's a very fast operation. I think in the first paper where we showed the reset of a resonator state, it was below what we can measure actually with our instrumentation at the time. It was below 4 nanoseconds. Of course, what's the fidelity? That's another question. But in principle, we believe that this is something that can be extremely fast.
Okay. Since there's no questions in the Q&A box, I'll just continue because I have a few more.
Okay.
So I was wondering how you price your products, and in these projects that you do with partners, for example, the VTT 50-qubit computer, do you try to make money on every sale, or are you happy to also take a loss to build up a customer base?
Yeah, that's a very good question. Of course, with any first customer case, you typically don't earn anything, and you earn through the actual value that it brings to the company instead of the amount of funds that comes in the company. And in our case, it is there's no exception to that. We are of course, at the same time, developing the technology in-house with whatever funding we get through this project, and at the same time, together with VTT, developing their technological know-how, which I think will be a win-win situation for the future of the quantum, at least in the Finnish ecosystem. So, so in terms of the pricing of the quantum computers, that's another a good question, because from all the major quantum computing calls that we have seen so far, there's always some customization here and there, and of course also the specifications, they are very different, and therefore the pricing will be different. We try to of course keep the margins high, but at the same time it's not very easy, because this is not like a really well established product where you can just make 10 of them and then figure out, okay, what's the cost price, but you are making every one of them at the same time. So you have a lot of this non-recurring engineering costs in there, but at the same time we try to, after calculation of the values it brings to the company, not to make a loss.
Okay, thank you. Then I was also wondering, maybe this is quite a general question that you get probably asked a lot, but the scaling up from 5 to 50 qubits is supposedly pretty hard. So what do you think are the main challenges for you guys, and how do you address those?
Yeah, there are many fronts to this. Of course, one of them is like, if you get 50 qubits, what will be the quality of the qubits? If you want to maintain the quality or make it even better than the system you have at 5 qubit, then already that's a very huge fabrication or engineering challenge there. And of course, at the same time, if you want to control so many qubits at the same, you need to have like really integrated control hardware and software, because the instrumentation itself is quite expensive if you just buy commercially, and you kind of have to work with your partners to see how you can reduce this cost. And of course, finally, is that once you develop this, is there any sort of exploitation that you can get out of the systems? Like if you establish one system on premise at your own headquarters, and then another one to customer, and then if you move to the next phase of technology, what would you do with the quantum computers that you just tune up? Are you going to warm it up, or are you going to keep on opening up to other potential cloud-based customers?
Okay. Then I have a question that is maybe from an academic standpoint of view. We're always interested to know what everyone else is doing. So how do you balance, and you're having a postdoc as well, right? How do you balance this kind of idea to publish with the need to obviously maintain a competitive advantage and like don't give away your secrets?
Yeah, that's also a very, very good question. There are many layers to this. One, of course, is when you have some new inventions, are you going to keep it as a trade secret, or are you going to publish as patent? That itself already has a really big strategy going on there, because some trade secrets are more valuable, because there's no way, if you patent something, you let the world know, and there's no way that you can check your potential infringement anywhere in competitors' products. Then moving another layer is towards publication of this scientific results, and we, in our case, we think that, okay, if there's something that we can patent, we typically just patent first and then only publish the results, and sort of keep some of the really critical know-hows internal. But at the same time, as a startup company that are building this high level technologies, you need some sort of credential, right? You need all these really strong publications to show that you are not just a startup doing something random, but you are also really well connected to the scientific community, and we are always balancing all this. Of course, we have internal committees actually reviewing the process as we go, and these committees are quite I would say quite successful in working out the different risks and also rewards for different phases in this publication.
All right. Thank you very much again, Kwon.
Thanks.
Any more questions? So we're also right on time for the invited talk by Cambridge Quantum Computing. So I see Simon and Mehdi already here. And yeah, thanks again, Kwon, and you're welcome to stick around if you want to hear some more. Oh, I think you're muted, by the way. All right. And welcome, Mehdi and Simon. So now we have Cambridge Quantum Computing, and I see Simon is starting. So let me just quickly introduce our two speakers. So Simon McAdams started his academic career with a bachelor in biochemistry, and then moved on to tissue engineering for regenerative medicine in his master's, and finally graduated with a PhD in nanoscience from the University of Manchester. Today, he's the lead for the quantum chemistry product at Cambridge Quantum Computing. And I think Simon will talk about the quantum chemistry side of the work that you guys do. And Mehdi will talk more about the about the business side of a quantum computing software startup. Mehdi is an expert on high performance computing, and his academic background is in both physics and math at the University of Sherbrooke. He graduated in 2003, and he studied quantum mechanics and numerical simulations. He then went into high performance computing and joined IBM, where he worked for 14 years, after which he followed his passion for disruptive technologies and joined Cambridge Quantum Computing in 2020, where he is the head of business development and offerings. Anyway, so questions again go into the Q&A box. I think you have until 17:45, right?
Yeah.
Okay. Welcome.
Well, thank you very much.
Thank you.
Thanks for the introduction, and nice to meet everybody. And yes, my name's Simon, and as in the introduction, I'm the quantum chemistry product lead here at CQC, and I'm going to give you sort of a quick introduction to Cambridge Quantum, talk about our quantum chemistry activities and also some of our machine learning activities and what we're doing with our various corporate partners before I hand over to Mehdi, and then we'll have Q&A at the end. So without further ado, let's get started. So if you're not familiar with Cambridge Quantum, we were established back in 2014 as a spin-out from the University of Cambridge. So we're certainly one of the oldest quantum startups out there. And we started with just 2 people, but now we have over 150 people now in the company. So we're certainly one of the largest quantum computing startups out there as well. So we have about 150 people, and they're spread across the globe. So we have offices in the UK, in London, Cambridge, and Oxford. We have teams in the US and the East and West Coast, a team in Japan, and we just opened up an office in Germany as well. So we are purely a quantum software company, and we develop hardware agnostic enterprise quantum software. It says here that we are independent, and we certainly are, but you've probably seen maybe on your LinkedIn feed that CQC and Honeywell Quantum Systems announced last week a merger. So we will be combining with HQS to form a new entity. So we will become by proxy a hardware company as well. But right now we are purely a software company, and we build software that leverages today's NIST devices for different applications. So this is our software stack. At the very center of our stack, we have our quantum software development platform called Ticket. And this allows us and our users to be both language agnostic and hardware agnostic as well. And I should mention the Honeywell merger won't affect our hardware agnosticism, so we will remain fully hardware agnostic even after the Honeywell merger. So I won't touch much on Ticket today because Mehdi and our quantum evangelist, Mark Jackson, will be speaking about Ticket on Friday. So Ticket, like I said, is at the center of our software stack. And then on top of Ticket, we have our various application programming frameworks for quantum chemistry, machine learning, and optimization, which I'll speak about today, but also natural language processing and cybersecurity, which are a little bit beyond the scope of this presentation. I'll just quickly say that for NLP, this is by far our most nascent sort of application programming framework, but one that gets a lot of people very interested. It's kind of the team's led by Professor Bob Cook, who was at the University of Oxford, but joined CQC earlier this year. And they've kind of already laid the foundations whereby a quantum computer could provide a quantum speed up to NLP tasks where there's a need to understand the grammar and the structure of sentences. And they recently, or a few months ago, implemented the first QNLP experiment on a real quantum computer. And then we have cybersecurity. And this is, again, sort of kind of a separate division, but we can actually run a protocol on NIST devices to generate certified entropy that can be used to seed quantum safe keys for security applications. Okay, so then the next layer up, we have our collaborator use case. So in addition to developing software, we also work with various collaborators across various industries where we work towards quantum advantage for their particular use cases. And I'll discuss sort of each of these in turn, but it varies from, chemistry applications with Nippon Steel to, machine learning applications with Aker BP and DHL. But more details on that later. Okay, so first we will start with our quantum chemistry platform called UMIN, which, as you've probably guessed, stands for Eigensolver of Unitaries for Molecular Energies. And it is a hardware agnostic, Python-based framework that allows users, whether they are computational chemists or quantum algorithm developers, to really get sort of best-in-class results using NIST devices for their quantum chemistry simulations. So essentially, users can mix and match the latest quantum chemistry algorithms with different quantum subroutines and error mitigation techniques to run their quantum chemistry simulations on NIST devices and simulators. UMIN is, of course, integrated with Ticket, so UMIN takes advantage of Ticket's, circuit optimization and circuit qubit writing protocols, and really reduces the qubit requirements that are needed for quantum chemistry simulations on quantum computers. And as I kind of alluded to earlier, UMIN has been built with our Fortune 500 partners and collaborators across different sectors, from pharma to automotive industries as well. So something that's really fundamental to UMIN are these sort of fragmentation techniques that you can see in the bottom right-hand corner here. So these fragmentation techniques allow us to take relatively large systems and break them down into smaller chunks, if you like, and allow us to run those chunks on the quantum devices and then stitch the results back together. And it really means that we can start to tackle much larger systems than otherwise would be possible using sort of traditional quantum chemistry techniques. But more on that later. So this slide gives you an idea of sort of the workflow of UMIN. So starting on the left-hand side, we take some input, which can be a molecular material system up to about 30 atoms size. These fragmentation protocols that I mentioned on the last slide, they really allow us to tackle these large systems. If it wasn't for these fragmentation protocols, we'd only be able to simulate maybe 3 to 5 atoms on a NIST device. So once you have your system of interest, we then need to define that problem, and we define the problem using sort of a suite of classical chemistry drivers, and you can select from sort of molecular chemistry drivers or these periodic boundary condition drivers that allow us to tackle sort of solid state crystalline systems. And then we have various embedding protocols that I had mentioned previously. So once you've sort of specified your problem, or we call it, you've humanized your problem, you can then select from different algorithms, which you can see here. And so if you're familiar with quantum chemistry on quantum computers, you'll recognize these algorithms. So we can actually implement algorithms, new algorithms that appear in literature very easily within Human, and we even have our own sort of proprietary implementations as well. So then these algorithms are kind of broken down into sort of smaller subroutine protocols, which you find in this protocols and error mitigation module, where you can sort of mix and match your algorithms with different quantum subroutines and error mitigation techniques. Once you've done that, you can then send your algorithm to your backend of choice via Ticket. So whether it's hardware or simulator, you can then use Ticket to retrieve your results, carry out some post-processing steps to get your results of interest. And you can see some of those examples here on the right-hand side. So we like to make it sort of as easy and as quick as possible to really run your chemistry simulations on these devices. So as I mentioned, Human has kind of been developed in partnership with various corporates, and I just want to say a few words of what we've done with them. So we're actually currently working with Roche on looking at sort of binding affinities of small molecule drugs to various target proteins. So we can't really mention more than what's in the press release, other than say we'll hopefully be publishing this work in a few months time. We have published some work with Nippon Steel. You can find the paper in the bottom left-hand corner here. So the work that we did with Nippon initially is that we took the standard molecular VQE algorithm, which you traditionally use to find sort of ground states and in some cases excited states of systems. And we adapted that molecular VQE algorithm to solid state systems and allowed us to sort of benchmark this novel algorithm on different hydrogen and helium lattices. And we should have a paper coming out in the next couple of weeks where we take this molecular VQE algorithm that we've applied to solid state systems and then apply it to Nippon Steel's use case of interest, which in this instance is looking at iron crystals and benchmarking two different types of iron crystals. And then last but not least, we've also been working with Total for the last, well, it must be in the last 18 months now. And again, it's solid state chemistry, but we're looking at this time these metal organic frameworks, which you can use for CO2 absorption and storage. Although you can start to swap out for different gases if you're interested in H2 storage as well. So that gives you a flavor of some of the problems that we're working on and that you can sort of start to tackle within the Human framework. Okay, so moving on to our other application programming frameworks for quantum machine learning and optimization. And we normally group these two together because it's the same teams that work on these. They're based in London. So with quantum chemistry, I'm sure you're aware there's sort of a clear sort of exponential speedup that is attainable. With machine learning and optimization, arguably the speedup is less clear. You know, is it exponential? Is it quadratic? Do you require QRAM or quantum RAM? So an efficient way to embed your data into quantum states. So at CQC, we work with these things called parameterized quantum circuits, which are kind of like neural networks, but for quantum computers. And we have this review paper here that you can find with more information. But these methods are kind of general enough that you can apply them to different techniques that you'll be familiar with. So we're interested in supervised and unsupervised learning. Generative modeling is a big part of what we do. Also sampling problems like Monte Carlo as well. These are just some of the things that we focus on, and also reinforcement learning as well. So some of the work that we've been doing with some corporates includes some work with Aker BP. So this is a supervised learning problem where they supplied us with this synthetic data set. You can see here on the left-hand side. So there's about 10,000 data points, 2 different features, 3 different classes. So you can imagine a pipeline with oil and gas flowing through it, and the different relative velocities of the 2 phases gives you smooth flow, wavy flow, solid flow, shown here in the green and the yellow and the purple. So we trained our model using these parameterized quantum circuits on 250 randomly selected data points, which you can see in the dark crosses here. And we found that we could get a test accuracy of about 87%, which was comparable to sort of standard classical SVM type methods, albeit this was in a small sort of toy data set. But nevertheless, we could match the performance of sort of classical techniques, and we only needed to use 3 qubits. So the next step is to see whether we could get some quantum advantage. So can we improve classification accuracies using quantum computers? So the idea is that we can take data, we can map it to high dimensional space, and this is something that is non-trivial to do with a classical device, and hence there could be some quantum advantage because we could start to tease out our data points and draw correlations that otherwise wouldn't be evident using classical devices. It's worth saying that there is a theoretical exponential speed up when it comes to data classification, but this requires QRAM or quantum RAM. We also recently announced work we're doing with Crown Bio, GSR, and this is looking at predictive biomarker analysis. So can we look at patient's genome and predict whether they would respond to a particular drug or not? So today, if you want to do sort of comparative genomic analysis, looking at 2 genes is tough enough. I think looking at 2 genes, I think there's 10 to the 8 different combinations. But when you want to compare 3 or more genes, suddenly there's 10 to, I don't know, the 20 different combinations. So the problem quickly explodes, and hence why it could be a good problem to look at using quantum devices. And then last but not least, we're also looking at, or we also did work with DHL and Honeywell. So DHL have this knapsack problem. So trying to optimally pack a delivery container with boxes and try to minimize the amount of air that is shipped in these containers. So they wanted to kind of tackle that problem in a quantum device. And Honeywell have this H1 device, which is the most powerful device that's been sort of measured to date, this 10-qubit device. And they wanted to showcase that device. So CQC kind of sat in the middle and sort of facilitated that workflow to implement this knapsack problem on a quantum computer. And you can actually go to the DHL website. I think it's called the Future of Logistics Masterclass to actually see the work that we did. But to summarize that, we found a way to sort of embed the problem. So you can imagine spin up of your qubit means include the box in your container, and spin down of the qubit means discard the box. And the sort of the lowest energy state of these qubits gives you the maximum weight that you can pack into a delivery vehicle. And again, this is a toy problem, so we added different constraints. So you can imagine trying to stack a 1D stack of boxes inside a container. But nevertheless, we showed it could be done. And I guess the next step is to see whether there would be a quantum advantage using a quantum computer to tackle this problem. And last but not least, some of the work that we just announced with DLR. So this is looking at nonlinear partial differential equations and whether we can run these on this devices to tackle lithium-ion battery simulations. So DLR currently use nonlinear PDEs to simulate lithium-ion batteries. And so they want to see whether they could use a quantum computer to do the same. So 1D simulations are kind of doable right now classically, but 3D simulations are kind of pushing the limits of what you can do classically. So we anticipate that quantum computing could potentially be useful for 3D PD simulations in the future, but that's what this project aims to find out. And you can find a paper in the bottom left-hand corner here. This is some work that one of our scientists did, Michael Lubash, looking at nonlinear PDEs on NIST devices, and this is what this work stems from. Okay, so before I hand over to Mehdi, I wanted to say that if you want to learn more about Ticket or Human, please contact us here. If you want to be considered as a human beta tester, which we're currently doing, please go to our GitHub page and you can find the human support email and drop us an email. Also, read our publications, follow us on LinkedIn as well, and visit our YouTube channel as well. So thank you, and I'm going to stop sharing and hand over to Mehdi, and yeah, we'll see each other again when we do the Q&A. Thank you.
Thank you, Simon.
Thank you very much, Simon. Let me share my screen. Here we go. Can you all see my screen? Perfect. I mean, thank you very much again for the opportunity. It's a real pleasure to talk about productization and commercialization of research. That's what it is at the end of the day. So let's start. So some context first, and that's the Cambridge quantum use case. So we, as Simon presented it, we have all those frameworks like programming framework, or we can call them research frameworks. Some of them are already consumable by end customers. That's the case for Human. And the underlying, I always call it my concrete slab, that's Ticket. So Human is very special in the sense that we're going through beta testing right now, and it really looks like a product. One frameworks for quantum machine learning and quantum optimization are still frameworks that can be used and leveraged internally in order to deliver a research output to end customers, but not ready yet for final customer consumption. And QNLP is emerging, so we'll see what it looks like in probably 1 year or 2. Now, that's the full stack, as Simon mentioned it. So it completely makes sense to consider all the moving pieces in our framework, and all of them are interconnected. So Ticket is extremely interesting because as it is connected to every single programming framework, every single time you improve Ticket, then all those frameworks will benefit from this improvement. And then the collaborative use cases are absolutely critical because that's how you get basically feedback from customers and the market. And again, we are completely backend agnostic, so that also lets our customers to find out how one specific algorithm that was tuned for their specific use case would behave on different hardware platforms, which is quite critical. Now, let's say I am a PhD student or a postdoc. I have a wonderful idea. What's next? So next is really, how do you make this idea fly and be accepted by the market? So you need to go through like multiple steps. And so we've identified that CQC, first it's productization and commercialization. So we are lucky because with Ticket, we have the foundation. And again, that's why I call it my concrete slab. So we did build the foundational layer that is common to all frameworks. Again, hardware agnostic, and it also connects existing frameworks with added value, like for example, circuit optimization and the combination of circuit optimization and noise mitigation, or the ability to actually not ask anyone to learn a new framework from scratch, but end users can still use whatever they know. Like the best example would be Qiskit in this case, and then insert Ticket on top of Qiskit in order to benefit from this added value. So foundation, it's done. What would be the next step? So again, all those frameworks, and I call them frameworks because most of them are not product yet. And the exercise is really to go from a framework that you can consume internally in order to give value to your customers, and through co-development. So why co-development? So usually when you start building a product, like any product that you can see on the market today, you need to go through some, again, exercise trying to find out, okay, so what will add value for one specific customer, and how do you insert this into your roadmap? And you never know if it will be a full success because, I mean, market studies are not 100% accurate, never. So co-development is actually really cool because in this case, you work with one very specific customer and you are 100% sure that you are on target. So that will allow you to develop specific features for your future products. And also the cherry on top of the cake that you get as a startup is you can also be a bit picky in the sense that if you get customers across multiple verticals, and then you get a good idea of the sizing of those verticals, it becomes obvious that you really want to put all your energy working with a customer that is attached to a vertical that is, I don't know, size 3 billion versus a size of, let's say, 500 millions. Then what it allows you to do as well is to go through immediate monetization. And usually when you develop your product, I mean, you're not making money. That's a given. You will be making money once the feature is added to the final product, and then you sell this product. In this case, again, the co-development phase, we're talking about research contracts, especially in the quantum space. So you can actually make money right at the beginning, which is always good. And also you create IP, which is even better. The other very good thing that you get through co-development is what I call stickiness. At the end of the day, if you are a customer and invest in working with a startup for developing what will be the product that you need, the chances that you drop the product once it's ready are like super low. So that's what I call stickiness. The next step, and this is not an easy step, is how to transition from frameworks to products. So at the end of the day, you really want to have your products to be consumable by end customers. And what you have at the beginning with co-development is a framework that may be used by very specific customers, but it's not a product yet. And that's this transition that is absolutely essential, because then it will give you sales enablement, but also partnerships enablement, which will be critical for the scaling part. The next step, of course, is commercialization of those products. And it's all about being able to execute on a streamlined sales process. Now scaling, I mean, everybody's quite far from this one, but the idea is really that through prioritization and partnerships, then now you have a product not only that is consumable by end customer, but that is consumable by partners. And you may be like super good at research, but not really good at, let's say, UX and GUI. So you can partner with specific companies who are extremely good at delivering end products, who can leverage your, at the end of the day, algorithms. And the cloud consumption especially is really in the scaling part. So I did put at the bottom like two zones, enablement and engagement, and that's really what it is. You enable your startup during the first 3 steps, foundation, co-development, and productization, and then you can fully engage with customers during the last 2 phases, commercialization and scaling. So the other thing that you can get from this diagram is also that during the co-development phase, for example, like at the end of the day, you still need to sell something, and that's your research engagement. So you need people who are experts in specific verticals to do that, because you need to establish the trust with the final customer in order to first pique their interest and then demonstrate that going through this co-development phase will give them something that is valuable. And at the end of the day, what is valuable for our customers is through these engagements, they are quantum enabled, like they will learn, because all the time, almost the only research teams that they have are classical research teams. So that's the first thing. And then they will get a very good and accurate idea when you combine the research engagement with the fact that we are hardware agnostic, so we can actually benchmark multiple technologies. And if you put these together with the official roadmaps from the hardware vendors, then you end up with a pretty good idea when you can reach quantum advantage, which is quite essential for our customers, because not only they know or at least they have a good idea when they will be able to extract commercial value from quantum computing, but that also gives them a very good idea when the competition will also be able to leverage quantum computing techniques. So in the pre-engagement zone, again, it's all about early monetization, which is quite essential for a startup, because you want to be a bit independent of funding, and that's one way to do it. Now, how does that translate in terms of organization? So that's basically the existing functional org chart. That's what everybody starts with. So you have one function that is just lead generation. I mean, you need to know who are the main players for specific verticals, who do you need to talk to and engage with. So that's the lead generation piece. And then opportunity owners are people who are going to negotiate and sell these research engagements. So that's really the co-development phase. So once you have frameworks very well identified, then the key is first start thinking about the prioritization. And that's why this opportunity owner function is now attached to a framework ownership. So typically a framework owner will be the product owner once prioritization is achieved. He or she is also typically an expert in his or her field. Like, I mean, Simon is the best example, because once you engage with customers, you need to first speak the same language and also have a pretty good idea of what are the pain points they are facing. Then, in order to be more efficient and more accurate, you absolutely need to have a team up between lead generation and market intelligence. The example I always give is, I mean, take any of our customer, Total, for example. So Total is a massive organization. And if you know exactly or precisely what are their research budget, and all of this for the main companies are publicly available, you know which team is doing what inside Total or Roche or whoever is your customer, then you can also identify multiple opportunities, and especially when you have multiple frameworks. So that's basically, it's building some kind of topographical map. Then the evangelist is really the function of pushing the branding and the technology awareness throughout the market and the main players. Then, of course, lead qualification, framework owner, and then I added in this case a new function called relationship manager. And that's really the person or the function that will help in not only making sure the delivery of these research engagements are successful, but also establish a very strong partnership with our customers and any customers that a startup may have. Because at the end of the day, you want to deliver some kind of research output, added value, but you also really want to be seen as a trusted advisor. And that's the function of the relationship manager. So that will be essential through the co-development and prioritization. Now, how does that scale? So that's the final diagram. So we still have this lead generation and market intelligence, the evangelist, but now we have framework owners and opportunity owners per framework. So what does it mean? Actually, it means that if you want to get more deals, then this becomes a team with still the same function. If you want to add a brand new framework like QNLP, for example, then you just scale it up, scale the organization horizontally in this case, and add a brand new framework here. Once you go through the full prioritization, which is the case for a human, then it's time to split the organization. So the framework owner will become a true offering manager or product manager, and you're able to split the organization and have the opportunity ownership piece of this function to be pushed into the sales organization. And then it's really like a split, sales on one side and then product on another side, so that it starts looking like a standard function organization. And I mean, all the numbers are, I mean, typical, like conversion rate of 30%, upsell 20% of the contract yearly. So that's what you can find in the literature. So more deals or more leads, let's put it this way. You add people there, then you will have to be able to handle more deals. So you add opportunity owners there. And that's very nice because you need only one framework owner, but you can add as many opportunity owners as you want to. And those all opportunity owners will then move to the sales organization. And it's the same for all frameworks. And what's nice as well is they are independent. So human, for example, can be first. That's absolutely not a problem. And then followed by the QML and optimization finance pieces. And again, you get more customers at the end of the day, so you can beef up the relationship manager team. So that's fully scalable, both sides, vertically and horizontally. Now, as a startup or as a potential founder with a wonderful idea, then there's lots of questions that you will have to find answers to. First, IP. So what do you want to do with IP? How do you want to make sure that you keep your IP so you can build on top of it? And then you will get questions from your potential customers, like because they also want access to this IP. So that's one of the big questions. Then consulting. Do you want to do consulting, like to bootstrap the company, or do you want, like day one, to clearly state that no, I'm not going to do consulting. I'm going to go on down the product path. So this will have an impact on funding, for example. Then what about open source? So open source versus closed source versus hybrid. So that's also a very good question. We saw like very good example of open source projects. I mean, the first that comes in mind is Qiskit, but there's also Penny Lane from Xanadu, and that's a question that you will have to answer. Then commercial engagements versus public funding. That's also a very interesting question because you can actually apply and then get public funding. That's one thing. Then you're tied to specific projects. But if this public funding at some point, I mean, it's limited in time. When if you do commercial engagements like this co-development step in the life of the startup, then as long as you are relevant and add value from a customer point of view, you will get some revenue stream, which is always good. It's permanent and it's really tied to how good or how relevant you are for these specific customers. And again, you can spread across multiple verticals just to diversify your, let's say, portfolio. Free POCs. So that's one thing that comes up every single time I talk to startups. The big question is, okay, I'm a super young startup. Should I do free POCs in order to get some publicity because I work with like one of the big player in one specific vertical? I would say be extremely careful about those ones, because what happens is every single time you give away something for free, it will lose priority. So as a big company, I don't know, let's say a bank or a big pharma company, they are always engaging with startups and doing POCs. So let's check one very specific use case. You're a big company and you have two POCs, one that you paid for, and all of them have a specific timeline. One that you paid for, and of course you're involved, you have to do something. And another one that you got for free, that is maybe super interesting, but it's free. So when you're getting closer and closer to the deadline, as a big company, you paid for something and you have to deliver something again. You're not going to drop this one. You're going to, if you're late, you're going to put resources on the paid POC versus the free POC. And what happens lots of the time is, you have a wonderful POC that you offer to one big company, hoping for some basically marketing outcome, but it's dragging and dragging and dragging. And that's really the danger with free POCs. The next question is when to collaborate with academia, or maybe not. So it comes down to, and that's a very funny situation, because almost every single university has different IP policies. And it's really tied to IP policies. You don't want to collaborate with academia if academia takes basically all your IP. So that's not a good deal. If it's all about sharing the IP or doing something together, definitely yes. And especially if you can leverage some funding, which is the case in Canada, when you have one customer, one startup, and one academic entity, then you can apply for funding from the government and basically get, let's say, a PhD student or a postdoc half of the price, because it's half funded by the government. And it's lots of countries have similar programs. Then incubators. So should I go and be part of some kind of incubator stream? And what I have in mind right now is CDL, Creative Destruction Lab in Toronto, and their quantum stream, which is the only quantum stream available today. That's a good question. That will give you lots of things, lots of input, basically coaching from from experts in their fields, from business to science, and all those questions. I would say, as a startup, you're better to have answers to those questions before you do any move. And it's all about executing on a plan that is not studied, but you absolutely need to be agile. Another thing that I keep saying is there's no better way to find out if your product or your idea of a product is valid and will add value to specific customers. Nothing better than trying to sell it. If you try to sell something 10 times and you're just not successful, it means only one thing. Even if it's a wonderful idea, the market is not ready for it. And if the market is not ready for it, that's not going to be a success. So it's a wonderful way to get feedback from the market, and also make sure that you stick to one specific or multiple verticals, keep adding value, and then it's this actually wonderful feedback loop, and that's the only way to get products that will stick from my point of view. So that's it for my presentation. If you want to reach out, so I'm always available on LinkedIn, or you can ping me at CQC there. So that's my email address. And again, thank you very much for the opportunity. And if you have any questions, let's go.
Yeah, thank you, Mehdi, and thank you, Simon, again, for the great talk. Just before I forget, I was wondering if you could share the slides with us so we can distribute them afterwards.
Yes.
Thank you very much.
Yes, that's absolutely not a problem.
And then we have a question in the Q&A. If, Simon, you could elaborate a bit more on the fragmentation technique. I think DFET was the name. In the human framework, like what happens at the boundary of the fragments, and maybe how big are the molecules that you can tackle?
Sure. So I'll preface this by saying I am an experimental chemist rather than a computational chemist. But from what I understand with DMET, for example, so you take your molecule, you split it down into sort of 5-qubit fragments, say, and then you take a fragment and you're going to perform VQE on that fragment. And in terms of the boundaries, the other fragments in your molecule make up a kind of effective bath that your fragment sits in. So say you had a sort of a sheet of graphene. So you have 4 atoms in a cell, so that's 8 qubits. So you can solve each fragment 8 qubits, 10 times. So you only need 8 qubits to simulate that graphene sheet. But if you wanted to simulate using without using DMET, you need about 80 qubits, which of course is completely infeasible on NIST devices, whereas you can certainly do 8 qubits today. So that's DMET, and then the other techniques include QMMM, which are analogous to the QMM methods that you use classically, but in the quantum computing version, the QM portion is performed using the quantum computer with a high level of theory, whether it's FCI methods, and then the MM part would be performed with some classical approximation using, I don't know, force fields or empirical methods.
Excellent, thank you. I have also a few more questions. Maybe if I can ask you, maybe you mentioned a few times this co-development and building your own products kind of trade-off. How did or does CQC balance that you, basically, if you co-develop something with someone, like it's easy because you're on point, but also you give them IP and you don't end up with maybe your own product.
Yeah, so what you really want to do as a startup is you want to keep the IP, and what you can do is, and it's the negotiation phase with the customer when you sell this research engagement, you can say, for example, you know what, I'm going to keep the IP, but whatever the outcome of the research engagement is, we will license it back to you. So it's a win-win situation, because as a startup, you own the IP, so you can build on top of it. But as a customer, even if you don't own the IP, you can actually also build on top of the research output. So on both sides, you can. There's an evolution path that is possible. And some customers. So I'm not saying it's easy. It's actually a very difficult negotiation exercise, because some customers can say, for example, you know what, we really want to make sure that our competition is not going to get access to this. So we want you not to, for example, work with direct competitors for a specific period of time. So that can happen. That's also quite usual.
Okay. And then maybe also on the business side, like what do you tell your customers about the perspective on hardware? Because I mean, you're building software for devices that don't really exist yet.
So we have partnerships with hardware vendors, like the big ones, to be honest. But we also have partnerships with emerging hardware startups, and that's exactly where you have to articulate something, because most of them are not ready yet. I mean, if you go through what exists today, you have companies like, so you have AQT, you have Honeywell, you have IBM, but you also have like IQM, and you have Archer Materials, for example, in Australia, that is like right at the beginning. But you also have Pascal, for example, in France, or Alice and Bob. Like, you have many possibilities. But what you can always tell your customers is, you know what? Whenever those small players are going to be ready for running these calculations, we will be ready as well, and you will be ready as well, because of this underlying, in our case, it's ticket. But we won't have to recreate the algorithm, use another framework to encode it, and so on and so forth. So in terms of agility and actually being able to very quickly react to new hardware platforms, that will benefit the end customer and yourself as well as a startup.
Okay, cool. And with respect to the time, maybe one more question from the Q&A. if you could quickly comment on such non-competition clauses you just mentioned, and in which cases would they be acceptable?
So to be honest, it really depends, and that's also why as a startup you need to be like extremely agile, because if, let's say, for example, you sign an agreement with one specific customer, this customer asks you not to work with one of their competitor on this very specific subject, then it's the question is it acceptable or not? And then depending on the duration of this, basically the time, you cannot execute on something equivalent with another customer. So what's, for example, the hardware roadmap? Because if you're tied to only one customer and you cannot come up with a product, basically, but at the same time, it is expected that given the state of the hardware in, let's say, 2 years, someone will get quantum advantage in this field, that's not going to be good for you, because your own competitors may not have these all those strings attached and may be able to move quickly on this vertical. So it's moving extremely fast. Let's put it this way, and it's not easy because we're talking about years. It's not 6 months. It's usually years. And it's all about assessing the market as a whole, hardware and software. And that's also where the market intelligence comes into play. Like you just cannot run full speed blind. You have to see what are the obstacles, basically.
Great, thank you. Then let me thank you guys again for the fantastic perspective on the business side of quantum computing. If anyone in the audience has more questions, we'll forward you the slides, emails, and you saw the emails as well. So feel free to reach out to CQC. Yes, so we'll see Ticket in the hands-on programming session on Friday. And now we have a poster session in Gather that you guys are obviously invited to check out if you are interested. I think we send you the link as well. One of the emails. Okay. And yes, this concludes our program for today. And yeah, so check out the poster session. And I would like to ask all the poster presenters for the poster session 1, you can find yourself in the leaflet that we send out, to go to your posters and present it to everyone who's by. So if you can hang around at your poster and explain it a bit. Thank you very much. And yeah, then see you in the poster session or see you tomorrow.
Thank you.
Thank you.
Bye.
Bye-bye.
Bye-bye. The recording's off.
Yeah, I just turned it on.
Okay, thanks.
Good. I'll share my screen.
Should we just stop it? At least now there's like a few seconds of schedule and
Exactly.
yeah.
People can see it.
Is it me? No, it's you, right?
Now, okay, I'm on.